In this tutorial, we'll look at some common questions in the topic of electrochemistry. Electrochemistry is a feared topic amongst students, but if you were to revise the topic sufficiently, you will find that the questions are pretty recurring, the questions are pretty routine. So what is required in a typical electrochemistry question is to be able to predict which ions are discharged at the respective electrodes, to be able to write out the half equations, and to predict the products and observations at each electrode. Later part of the chapter, we will also look at the applications of electrochemistry or electrolysis, as well as simple cells and fuel cells. So as mentioned, this is a common type of electrolysis question where you are asked to predict what happens when a specific electrolyte is electrolyzed. Now, most of the time, the electrolyte given in the question is one that you would have already encountered as a case study in the syllabus. So very rarely would it be something that you have not seen before. But even so, as you will see later, we can just apply the same principles and arrive at the correct answer. So for the sake of this, for learning, I will go beyond answering this question to show you the typical questions that will occur, that will be given for questions like this. So the first electrolyte that we're looking at would be concentrated aqueous sodium chloride. You're asked to predict the product at the anode and the cathode. So there is a fixed approach to doing so. And the fixed approach goes something like this. So step number 1, you need to identify the ions at the anode and ions at the cathode. So first thing to remember, anode attracts N ions. So anode is positive, it attracts N ions, and the N ions in your electrolyte would be your chloride and hydroxide. Next, your cathode attracts cation ions, so it is negative, and the cation ions that are present in your electrolyte would be sodium and hydrogen. The next thing to do is that when you have more than one ion at a particular electrode, how do we know which ion is preferentially discharged? We make use of the electrochemical series, and the rule goes like this: the lower an ion is in the electrochemical series, the easier it is to be discharged. So at the cathode, when we compare your cation ions, hydrogen ion is way below that of sodium, so it will be preferentially discharged. At the anode, your hydroxide is below chloride. However, in one of our case studies, we learned about concentration effects. When you have a concentrated electrolyte, concentration would only affect the discharge of ions at the anode, and specifically for your halides or your chloride, bromide, and iodide. So in this case, when you have concentrated chloride, even though it is slightly above hydroxide in the electrochemical series, it will be preferentially discharged. Once we have established which ions are discharged at the respective electrodes, now we can write the half equations for the reactions that are happening at the anode and the cathode. Anode is the electrode where oxidation occurs, so your chloride ions are going to be oxidized to form chlorine gas. At the cathode, this is where the electrode for where reduction occurs, your hydrogen ions are going to be reduced to hydrogen gas. So what I've done is to write the half equations for the reaction at the anode and at the cathode. Now with the reaction, with the half equations, actually even without the half equations, you should be able to predict the products that are formed already. When chloride is discharged at the anode, it will be oxidized to chlorine gas. When hydrogen is discharged at the cathode, it is reduced to hydrogen gas. Another common thing that the question will test you on is on observations. So if we were to look at the products that are formed again, you would see effervescence at both electrodes. And other than that, you would be able to recall from periodic table that chlorine exists as a greenish yellow gas. So when you electrolyze it for a long period of time, you may see a greenish yellow gas appearing at the anode as well. Now let's apply the same steps now to the next electrolyte, which is your concentrated aqueous potassium iodide. So once again, let's go through the steps. We have the anode and the cathode. Step number 1 is to identify the ions at the anode and the cathode. So at the anode, it attracts anions. We have iodide and we have hydroxide. At the cathode, we have hydrogen and we have potassium ions. Step number 2, we need to determine which ion is preferentially discharged, and most of the time we rely on the electrochemical series. So at the cathode, hydrogen is lower. It will be preferentially discharged. At the anode, once again, you would see this term concentrated aqueous potassium iodide. So as mentioned earlier, concentration effect would favor the discharge of your halides. Halides meaning chloride, bromide, and iodide over hydroxide. So in this case, your iodide will be discharged. Step number 3 is to write the half equations for the reactions at the anode and the cathode. The half reaction for the reaction at the cathode is the same as above, so I will not be writing for that. But at the anode, what is happening is that your iodide ions will now be oxidized to iodine. Most likely it is going to be aqueous, it's going to be dissolved in water. And in this case, we would see iodine. I think it's perfectly okay for you to write either aqueous or liquid. Iodine is sparingly soluble in water, so it's okay for you to write as liquid or aqueous. At the cathode, again, it will be hydrogen gas. So the last thing to do is to describe the observations. So for potassium iodide, you would see effervescence at the cathode, and you will see the appearance of either a brown solution or brown liquid appearing at the anode. Now, a common question is how do we derive the half equations? If you are good at balancing charges and atoms, you can always do it on the spot, but I would recommend that because there are only very few half equations that you will encounter in this chapter, so it will be good if you can just memorize the common ones. In this question, we are looking at another electrolyte, which is your aqueous copper 2 sulfate. So this is one that we have encountered in our case studies before. And in this case, we are using graphite electrodes. So graphite electrodes would be your inert electrode. It's not going to take part in the reaction. Now, even though it is a case study that we have encountered, there's no need for you to memorize. I hope you can see that by going through the same few steps, you will be able to arrive at the answer fairly easily. So at the positive electrode is going to attract your anions, and the anions in your electrolyte would be hydroxide and sulfate. So in this case, hydroxide is lower in the electrochemical series, so it will be preferentially discharged. when hydroxide is discharged, it will be oxidized to oxygen gas. Now this is one half equation that I would strongly encourage you to memorize because it's not easy for you to derive on the spot. So this is the half equation for the oxidation of hydroxide ions to oxygen gas. At the negative electrode, which will attract your cation ions, you would have copper and hydrogen ions. So in this case, copper ions are below hydrogen, so your copper ions will be reduced at the negative electrode to form your copper metal. So what would you observe at the positive electrode? You will be observing effervescence. And what will you be observing at the negative electrode is that you either see a pink solid forming, or you can describe it as a reddish brown. So the pink or reddish brown solid refers to your copper metal. So what happens to the electrolyte? If you take a look at the electrolyte, at the start, if you have aqueous copper 2 sulfate at this stage in your revision, I hope you can remember that copper 2 sulfate is a blue solution, and it's a blue solution because of your copper 2 ions or your aqueous copper 2 ions. In this particular electrolysis, your copper 2 ions are being discharged, meaning there will be lesser and lesser of it remaining in the electrolyte. So as a result, the blue color will either turn to colorless if you electrolyze for a long period of time, or it will just simply fade. So the blue color becomes lesser in intensity, or it would fade, or it would become colorless. Now another extension to this question is this, that if I were to add universal indicator into the electrolyte after it has become colorless, what would be the color of your universal indicator? Now the answer is that your universal indicator would now be red. Now how do you determine what is the color of your universal indicator? Is this, that if you look at the ions remaining in the electrolyte, meaning those that are not discharged, you have hydrogen, you have sulfate, which makes the solution, which makes the electrolyte sulfuric acid. Okay, or if you just look at the hydrogen ions remaining, it would mean that the solution is highly acidic, therefore it would appear red when universal indicator is added. For this question, we are looking at the electrolysis of a particular electrolyte before and after electrolysis. And for this question, if you don't know what to look out for, it can be pretty complicated. So what you need to look out for in this question is that number one, a gas is produced at both your anode and your cathode. Second, the volume of gas produced at the anode is half, okay, or less than the volume of gas produced at the cathode. Now, if you have remembered the case studies well, you would remember that in one of them, we saw that the volume of gas at the cathode is 2 times that the volume of gas at the anode. That is when your water is broken down into oxygen gas and hydrogen gas. Now from the overall equation, we can see that the hydrogen gas at the cathode is 2 times the volume of oxygen gas at the anode, because the mole ratio is 2:1. And since we are looking at gases, the mole ratio is the same as the volume ratio. So in this case, the question requires you to determine, just based on the observation that the volume of gas at the cathode is 2 times that of the anode, to deduce which electrolyte it could be, and that would require you to tap on your prior knowledge of the case studies that we have gone through in the syllabus. Now, first and foremost, ethanol would be out because ethanol is not an ionic compound, so it is not a suitable electrolyte. Your circuit wouldn't be complete. Now, for the remaining three, for aqueous copper 2 sulfate, if you can recall from the last question, at the cathode we get copper solid forming, so there's no gas form at all, so A is wrong. There will not be any gas forming at the cathode. For concentrated aqueous sodium chloride, in this case you will need to tap on your knowledge of the case studies. You will find that the volume of hydrogen and chlorine is actually 1:1. So in this case, the volume of gas at the positive and negative electrodes should be equal. So it is out. For dilute sulfuric acid, if you go through the example again, the overall equation, when you pass a current into dilute sulfuric acid, essentially you are breaking down water. So when you break down water using electrolysis, you will end up, for every 2 moles of water, you will get 2 moles of hydrogen gas and 1 mole of oxygen gas, which will lead to the observation shown in this question. For this question, we are shown 2 electrolytic cells. The electrolyte in both cells are the same. It is aqueous copper 2 sulfate. So we are also told that for experiment X, meaning the electrolytic cell on the left, the electrodes are inert, and for the electrolytic cell on the right, the electrodes are active, reactive electrodes in the form of copper. So the question simply states on which electrodes is solid metal deposited. So in our case studies of the electrolysis of copper 2 sulfate solutions, we know that a metal or your copper is deposited at the cathode, which is your negative electrode. So in this case, it is not affected by whether the electrode or the cathode reaction, the observation at the cathode is not affected by whether the electrode is reactive or inert. And in this case, we just need to look for the negative electrodes, which is electrode 2 and electrode 4. So this is where the solid copper will be deposited onto the electrodes. So the answer is C. For this question, we are looking at the electrolysis of 2 different electrolytes now. The first electrolyte is your copper 2 sulfate. The second one is your dilute sulfuric acid. Before we even look at the question, it is worth noting that these 2 electrolytes are the case studies that we have encountered in the syllabus already. Okay, so I cannot stress the importance of knowing the case studies in the syllabus well, because they are being tested in most of the questions. So the question is asking for what happens to the concentration of the electrolyte in L, which is copper 2 sulfate, and in M for sulfuric acid. So over here, very quickly, if you have already memorized or you are familiar with the case studies, when you pass a current into copper 2 sulfate, your copper 2 ions will be reduced. It will be discharged. And what happens? Your concentration of your copper 2 sulfate electrolyte will change. So the concentration will not stay constant. In the case of dilute sulfuric acid, you would recall that it's actually breaking down water. So as your water in your sulfuric acid is being broken down, you will get lesser and lesser water remaining, meaning the concentration of your sulfuric acid would actually increase, or the sulfuric acid will become more and more concentrated. So in both cases, the concentration will not stay constant. Now for electrolysis, most of the questions are qualitative, meaning they ask you to describe in words, but there are a few quantitative ones. This is one of them. So over here, what we see in the question is that we have 4 electrolytic cells connected in series. So when you have 4 electrolytic cells connected in series, the same amount of charge or the same current would pass through all 4 cells. Right? So another common type of question is that you will see the same amount of current or the same amount of charge. Essentially what it means is this, that the number of moles of electrons that passes through all 4 cells are the same. Okay? Next, the question is asking which solution would produce the greatest increase in mass of the cathode. So remember, in order for the cathode to increase in mass, it is usually due to an ion being reduced at the cathode. And for any ions to be reduced at the cathode, it must be below hydrogen, because this is an aqueous solution. Dilute meaning aqueous. So in this case, immediately we can rule out A. Alright, aluminium is above hydrogen in the electrochemical series, so hydrogen will be reduced instead, and we can remove lead as well. So the only 2 metal ions that are below hydrogen here would be copper, Cu2+, as well as silver. What happens at the cathode would be that your copper 2 ions are going to be reduced to copper, and your silver ions are going to be reduced to silver. Okay, now how do we then know what is the mass of copper or mass of silver produced? Is to recall this, that if a cell is connected in series or you have the same current passing through it, the number of moles of electrons remain the same, or the number of moles of electron that goes into both cells are the same. Okay, so let us assume a value of 1 mole of electron. If we have 1 mole of electrons passing through all the cells, the number of moles of copper that will be produced would be 0.5. Okay, why 0.5? Because you need 2 moles of electrons to form 1 mole of copper. So if I only have 1 mole of electron, I will only have 0.5 moles of copper. And the number of moles of silver will be 1. Now, once we have the number of moles, we can then go on to find the mass by multiplying by molar mass. So the mass of copper would be 32 grams, and the mass of silver will be 108 grams. So the solution that will produce the greatest increase in mass at the cathode would be that of silver. Another common type of question in electrolysis involves the applications, and it requires you to describe how you can use electrolysis for that particular application. For the applications of electrolysis, there are 3 of them. Let's do a quick recap. The first of which is in the extraction of metals, particularly the more reactive ones. We can electrolyze the molten salts to get the metal. The ones that are more commonly tested will be the purification. And the case study in our syllabus is the purification of copper. And the last one, which is also quite common, is that of electroplating. And again, in our syllabus, we learn how to electroplate a metallic object with copper. Now for applications 2 and 3, you will need to know the experimental setup, namely what goes to the anode, what goes to the cathode, and what electrolyte to use. So in this case, for This question we are looking at purification of copper. So you are given impure copper electrode and then you have a pure copper electrode. So the important thing to remember is this, that in purification, at the anode we use the impure metal or your impure copper. At the cathode you use the pure copper, and your electrolyte must be an aqueous solution containing the metal ion of the metal that is being purified. So an aqueous solution containing copper 2 ions. So you can use actually aqueous copper 2 sulfate. Since the question requires a labeled diagram, let us very quickly draw it. So this is a typical diagram. To represent impure, I'm going to use an odd shape, and then a pure, I'm going to use a nice rectangle. Okay, so remember the impure is found at the anode, and the pure metal is found at the cathode, and our electrolyte is your aqueous copper 2 sulfate. So if we were to have a setup like this, we can actually, what will happen is that in your impure copper, your copper atoms will be oxidized to copper 2 ions, and then the copper 2 ions in solution will then be reduced to form pure copper on your cathode, or pure copper on your pure copper cathode. What will happen to the impurities in your impure copper is that they will just simply fall down or be deposited at the bottom of your anode. Another application, as mentioned, is the electroplating of a metallic object. For electroplating, again, you need to remember the particular setup where the anode is the metal to be plated. The cathode must be the object that you want to plate, and then the electrolyte must contain the metal ion to be plated. So in this case, we are plating the key with copper, so you can see why the electrolyte is copper 2 sulfate. However, the question tells you that the key doesn't get plated. So over here, let's check the setup. You can see that now the key is at the anode. Okay, so for electroplating, the object that you want to plate the metal onto, you must put the object at the cathode instead of the anode. So all you need to do now is to reverse the electrical connections, and now your steel key will be found at the cathode. Now the last type of questions that we will get in electrochemistry is that of a simple cell or a galvanic cell, where we make use of a reaction that releases energy to harness that energy in the form of electricity. Now, how do we distinguish between an electrolytic cell and a simple cell? Is to look at whether a battery is present, or in this case, in a simple cell, since electricity is produced instead, we will use a voltmeter to measure the voltage between the electrodes. So whenever you see a voltage, it is related to simple cell. When you see a battery, is related to electrolytic cells. Now for simple cells, there are two main concepts that you need to remember. The first main concept is this. Number one, the electron flow from the more reactive metal to the less reactive metal. So in this case, in this question, first and foremost, we have established it to be a simple cell. There's a voltmeter. And then we have two different electrodes, zinc and copper. Zinc in the in the metal reactivity series, zinc is above copper, so it's more reactive. And we have just revised that in a simple cell, the electrons flow from the more reactive to the less reactive electrode. The second important concept in a simple cell is this, that the greater the difference in reactivities between the two electrons, between the metals used in the two electrodes, the larger will be the voltage produced. So in this case, the question goes on to say that your electrode 2 or your zinc is replaced with three other metals, and then they measured the following voltages and to ask you to match to the different voltages. So you see that there's a voltage of 0. That means that the two metals are the same. So this must be the one where your electrode 2 is copper. Next, we need to look at the three remaining metals, and based on concept number 2 that we have just revised, the largest voltage of 1.10 must be achieved with the most reactive metal amongst the three, and the most reactive metal would be your zinc. 0.78 is the second largest, that would be iron, and then 0.21 would be lead. For D, when metal M was used as electrode 2, it produced an even larger voltage than zinc. So what it means is that it must be more reactive than zinc. So over here, suggest a name for metal M. Let's try to recall the metal reactivity series again. We have potassium, sodium, calcium, magnesium, aluminium, and then we have zinc. So the metal must be one of the above. Personally, I will not recommend the first three. Why? Because if you look at the electrolyte, it's actually an aqueous solution. So the first three metals actually react readily with water. Now, can you use magnesium? I would say it's okay. Or you can even suggest aluminium as well. As long as the metal is more reactive than zinc, it would satisfy the condition and would produce a larger voltage.